let's roll back. So I'm Danilo. I'm part of the developer experience team in AWS. So we help developers be successful on AWS, and we also get your feedback. So if you have feedback about our products, we can chat afterwards, and I'm happy to bring the feedback back to our service teams. And today I'd like to talk about a different perspective about generative AI. So we saw the amazing things we can do with generative AI with John's talk. But there's some problems with generative AI, how it works with hallucinations. So I'm going to talk about how you can use a different approach with automated reasoning to mitigate hallucination with generative AI. So just to start, so the generative AI is changing quickly. We've seen how you can invoke models and get a response that can process the result. But currently, we've seen a big trend towards AI agents. And the idea is to go beyond the single model invocation. So with an agent, you still give normally a prompt, an input to the agent to get a result. But the agent is not just a model providing you the immediate result. It's normally some piece of software that can invoke a model, normally at first to build a plan. Hey, I give a question like, would you like to write me a blog post from this transcription of a podcast? The agent says, instead of replying immediately with the blog post, will say, hey model, how can I build a plan to do this? What is the information I need? And the model will return normally a plan with a list of tasks to do. And then the agent can also call tools that are external APIs that can allow to call internal APIs, public APIs. It can use a browser, it can use a computer. So maybe you can create a tool that gives you the name of the guest of the week, and then the tool will give back the right syntax of the guests so that you can fix them without having to do that manually. And this is typically called an agentic workflow. It's not fixed before, so the agent with the model will create some dynamic process flow that will be executed calling external tools and provide a result at the end or in the middle. Some agents are interactive, some agents run in the background, some agents have a human in the loop to validate the result. And currently we've seen agents used a lot in software development. So if you use any modern IDE, or if you use something like Amazon Q Developer, now you have an agent there that can do a change in your code, run your test, see the error in the test, and automatically try at least to fix the error and do that iteratively. And because agents are really an important part of AI engineering and software development, at AWS we launched an open source framework a couple of weeks ago. It's called the Strengths Agents. So it's not an AWS product. It's an open source framework that we launched together with other companies like Anthropic. And it allows you to create an agent with just a few lines of code. So this is an example, unfortunately, in Python. So you create an agent, and then you can start an agent with some question. And this agent will keep a session, and you can take a reply and ask other questions again. So it's very quick to use. By default, it uses Amazon Bedrock to invoke models, but it also supports other providers. So we have connectors for Anthropic API directly for OpenAI. We also support Light LLM, that is an open source tool that allows you to call a bunch of other providers like Mistral, for example. And we also support Olama, so you can run your local models, for example, on your Windows or Mac machine. And in that case, you don't have any cost. It just runs locally. And you can use that also as a development environment. It supports tools. So it has default tools that we provide, like a calculator, because models are very bad at maths, the current time, and the recurring problem. It can create and run Python code as part of the tool, so the model can decide, okay, to solve this problem, I write this program, I run it, and then I see it. Last time I used it, I asked this model to give me the summary of the news on a specific website. And it decided instead to go straight on the website because there's a connector. It decided, no, I write my Python code to download the RSS feed from the news site because it's smaller and faster. So good for him, and it worked well. You can also create tools as Python functions, so you can just annotate a function and then it's available as a tool. So this is a letter counter, unfortunately very complex problem for the current generation of models. The models don't see the letters, they see the tokens, so they normally don't understand the single letters of a word. So this is a way to solve that in case you have this specific need. You create a letter counter function and you say, hey, this is a tool, and then when you create the agent, you can put the tools or the functions to enable as tools. It also supports MCP, so you can connect any tool via MCP, and it can export an agent as an MCP tool so that you can connect your agent with your IDE or your applications with just a few lines of code. It supports multi-agents architectures. Normally it uses a code-first approach, so you create a tool and then the tool calls the agent, but it works very well. So it's very powerful, code-driven, very easy to use, and it's very light. So the first generation of this kind of frameworks, they have a lot of prompts inside the agent framework to manage the handling of how the agent should work. But we noticed that with current the new generation of models since Claude 3.5, you don't need to provide a lot of information. If you ask a question and you give tools, the model will just create the plan and do it by itself. So it's very light and easy to update. If you're interested, you can go in this URL and learn more. It's something that we are quite interested as AWS, and again, give us our feedback on these tools if you play it. Already have some feedback from Ryan. So, but even if you use the most advanced models, even if you use the most advanced agent framework, you still can have hallucinations, because that's the way these AI models work. So most of the models, they use an architecture that is called autoregressive. That means that they generate one token at a time, then you send back the full input plus the token, and they will generate the second token, and then you send this back again and again. And that's the reason why they are incredibly slow compared to any other internet architecture. And when they decide a token, there is like a probability distribution. So if you are unlucky and they choose the wrong token, then you can get a wrong path and generate something that is completely made up by the model. You can mitigate that with a lower temperature. Normally that means that the model will try to stay where there is more probability. There are other parameters that many models support, like top P and top K, that basically says keep only the higher probability, or take only this K, the top K results, and avoid the less probable results. These again are very good mitigations, but you still can have the probability of an error. So if you build, for example, a chatbot to decide if customers can have a refund when they make a purchase, it might work well 900 times out of 1,000, but then you can have edge errors that maybe some customers can trick it and find ways to get their money even if they're not eligible. So this is the kind of thing that we want to mitigate. And hallucination can be very subtle. So I'll give you just a few seconds. This is the ground truth document, and this is a summary generated by an LLM. Can you spot the hallucination here? It's in the name. So the original name was Marlo, and as I said, no, models are very tricky with letters. For some reason, it decided that in the summary, this name became Marco. That doesn't appear in the original document. So this is an example of a very small hallucination, but it can have an impact if you use that name in the result. How did we end up here? So I'm a very boring person compared to John, so I'll start from the origin of AI. And if we go back to the 1950s, it's when scientists for the first time got broad access to computers after the Second World War. And there was absolutely no idea of what to do with these things to make them thinking. So there was this idea of, oh, let's build thinking machines. And there were a lot of theories like cybernetics that is not that different from the modern agents, because it was the idea of creating feedback loop to self-improve, complex information processing, automated theory. But there was no terminology, basically. And then this guy, John McCarthy, who later invented Lisp, the programming language, John McCarthy said, oh, let's use a term that is generic and doesn't support any of this theory. Let's call it artificial intelligence. So he created the terminology. And in 1956, he created this very interesting event, the Dartmouth Summer Research Project, where he invited like 10, 15 people, bright people there. There was John McCarthy, there was Marvin Minsky, another pioneer of the time. There was Claude Shannon, who basically invented or formalized information theory. So if you ever invent a time machine, I think going back to this specific place could be an interesting time to be. And they actually thought that, okay, with all these bright minds, we spend 2 weeks, we'll probably solve the problem of artificial intelligence and create thinking machine. Actually, it was a little bit more complex than that. And what came out of this meeting was 3 different fields of AI. The first one is the connectionist, that they wanted to replicate the cognitive way the brain works. So the idea of the perceptron and then neural networks comes from this area. There were the probabilistics, who wanted to use probabilities and Bayes' theorem to try to estimate probabilities of things. There were the symbolic AIs. They wanted to use symbols and manipulate symbols with logic or formal logic to get results. And in different periods of times, each of these branch was advanced and the other was behind, and there were a lot of different things that happened. But currently, connectionists and probabilists, they merge into what we call modern machine learning with the neural networks and deep learning and now generative AI. And the symbolic AI evolved in what we now call automated reasoning. So this is the 2 terms that you find currently in literature. And this 2 approach can't be more different, because with machine learning, you normally have a large amount of data that are examples of what you want to predict. You go through a training process that will find the right parameters for your model. And then when you have the model, you can run inference and have predictions on the result. And the model can generalize this prediction to unseen data that is not in the training, but is not 100% correct. It can make mistakes. And with generative AI, these mistakes are the hallucinations. With automated reasoning, the approach is very different. You need very little data. The specific information you want to manipulate, like a company policy, a business process, a checklist, and you need to translate this specific information into a logical model. And when you have this translation into a logical model, then you can use symbolic reasoning to ask questions about this document or this process. And if the model is correct, so the assumptions are correct, the results are correct and are also accurate, sound, and transparent. That means that you also understand if maybe there's no possible answer, or if there is an error, the model can explain what is happening. So you have the explainability that normally you don't get from traditional machine learning. Quick example, let's say I ask you, I want to compute the area of a triangle. If I use machine learning, I will measure tons of triangles, and if I have a good model, I can find good parameters. I'm probably able to estimate the area of triangles with a good result, not perfect, but good. With automated reasoning, what I can do, I can feed the basic rules of geometry to a model, and manipulating these rules of geometry, the model can the actual rule to compute the area, and this, when it's found, is correct and works for all triangles. So 2 different approaches for the same problem. And this is how automated reasoning works. So basically, you have a system that has some logical statement to prove, and it will explore all the possible paths. And normally, it can only have 3 outcomes. Either it finds a solution, it can prove that there is no solution to this problem, or it can find out that you need more time and more computing power. This is really the basic of how this automated reasoning works, exploring the solution space and finding possible results. So to use automated reasoning, you need 2 things. You need the logical model, and traditionally that means that you need to hire a logician that helps translate a document in natural language into a logical model, working together with someone who understands the business context of the document. So this is very slow and complex. And then you have software that can explore all the possible states of this logical model applied to your data to find the possible solutions. And more recently, there have been a lot of good results in fast algorithms that can explore a lot of data very quickly and skip branches. But still, what happened until now was that using automated reasoning was so expensive that it was used only when failure was catastrophic. So it's being used historically for silicon design. So before, when you create a new chip, a new silicon, just before starting the physical production, you normally use a simulation with automated reasoning to validate that it works correctly. It's used in encryption when you implement a cryptography algorithm to be sure that the implementation is correct and there's no edge cases with your implementation compared to the baseline. Has been used in the design of spacecraft to validate the design of spacecraft before they are launched, with probably not optimal results all the times. And more recently has been used a lot with programming code, because programming code is a sort of formal language, so it's easier to translate to a logical model. You don't need a logician. So for example, this is an open source project, Daphne, that we as AWS contribute to. And Daphne is a verification aware programming language. Basically, the idea is that instead of writing the code of the critical section of your application, you write the specifications of what you want to build. And then Daphne can translate those specifications and compile them into your familiar programming language like C#, Java, JavaScript, and so on. And Daphne allows you to add verification code to the specification to be sure that the specifications are correct. Typical example is you have maybe a critical function in your application for performance. You start to optimize this function and it's much faster, but how can you be sure that it works exactly as the original function for all the possible edge cases? Normally you need to do harness tests, but sometimes the number of possibilities to test is just too big. It's impossible to do all the tests. So if you're interested in Daphne, there is a website and the GitHub repo here, but I'd like to show you a quick example. So this is how you can use Daphne. This is how you declare a function in Daphne, and this is a function to compute the Fibonacci number. And it's exactly the definition of Fibonacci number. It takes in input a natural number, in output gives a natural number. If it's 0, it's 0. If it's 1, it's 1. Otherwise, you need to sum the two previous Fibonacci number. So this implementation is correct by definition, but incredibly slow and memory hungry, because for every invocation you have two recursions. So if imagine the number of, and each recursion is probably computing the same Fibonacci number again and again, because when you compute this one, you will have this one and minus 3 and so on. So you're basically recomputing the same numbers again and again. So if you sit down and you write, this is a much better algorithm to compute a Fibonacci number without recursion. It's much faster. It avoids recomputing the same things. But how can I be sure that it's actually equivalent to this one for all natural numbers? So an infinite set of numbers. So this is a better implementation. And I can add this verification code to my Daphne definition. So I can add here, I want that this method ensures that B, the result of this function, is always equal to this Fibonacci number computed with the same input. So and this is a statement, it's not a test. I'm saying for all possible natural number, I want that the result of this function is equivalent to the result of this function. And then here I can also declare invariants, like I can say the I in the iteration here must always be between 0 and n, otherwise something wrong has happened here. I want the variables in the loop to always decrease at each invocation, so that I know that this function will always terminate, and there's not an edge case that this function will go on forever. And I can add other invariants as well. And if I do this, they can run Daphne verify with this code, and Daphne will tell me if these things, so this verification code, is correct as a proof for all possible natural number or not. If not, will also tell me what's the error. And then I can build this and with a target programming language, so it will be translated into, for example, C# or Python or Rust. And if we go here, we can have a quick look at the same code in in, oops, a little. So if you see this green bar here, is because I also have the Daphne plugin for VS Code. It actually just already ran and told me that that it ran. But otherwise, I can just, here I can do Daphne verify fib, and it will tell me that it's okay. And if I try to change something here, like instead of increasing by 1, I increase by 2, boom, it's found that this invariant is not respected anymore. Actually, this is not, okay, there are other errors. So it found all the errors, and if I also do the verify thing, of course, it will tell me exactly the same thing. So this is a different way of building a program. It's not something that you would use for all your code, but the critical part of your code. And for example, we use Daphne for the AWS encryption SDK. Is the encryption that you give to our customers to manage keys client side. So it's built with Daphne to prove that the encryption is correctly built and implemented, and then we use Daphne to compile into .NET, Rust, and all the different languages that customers actually use for this SDK. And we use automated reasoning a lot inside AWS. So for example, we use it with IAM access analyzers that can check your security configuration on AWS, with the VPC reachability analyzer that is used to understand if, for example, one machine in one VPC can connect to a database in another VPC. We will check all the possible network configurations. It's used by the S3 block public access. So when you create an S3 bucket, you can say block public access, and this will verify that all the possible permission on S3 at object level, at bucket level, at role level in your organizations. There's no possibility that someone not authenticated has access to content inside this S3 bucket. And again, this is a proof that we do with logic, so it's true, and it's not just a test. We use it with verified permissions. There is a way to handle permissions inside your application. So if you start to have a lot of if-then in your application to say if this user has this role, he can do this, otherwise he can do that, that's a good sign that you need a framework to manage user permission. And verified permission is a fully managed framework that does that for you. But we also open source the language and the evaluation engine. It's called CDAR. So you can use it without any cost with the open source version. And basically, we used automated reasoning to just verify that the language is formally correct, and then we use it to validate the security permission inside your configurations. And a lot of these tools that I mentioned, like S3 public access, IAM access analyzer, actually internally they use an internal service that we have at AWS that is called Zelkova. So it's not a public service that you find in the console, it's only internal. And basically Zelkova gets the request from these services, so from S3, when you enable block public access from the IAM access analyzer, they give all the information to Zelkova that will translate the question into logic, and it's then using a portfolio of solvers to find then the end result that in this case is always a yes or no. And to give you an idea, we use this system more than 1 billion times per day. So it's used by a lot of systems inside AWS to certify the specific configurations. But now I'd like to jump into the core of the idea. So I explained how automated reasoning works and how you can use it in different approaches. Let's see how you can use it with generative AI. So LLMs change the way you can use automated reasoning, because the LLMs are actually quite good in writing logic because they learn from all the content that is available. So they can quite easily translate natural language into a logical model. And then if you have that done, you don't need the logician. You only need the person who understands the business context of the document. So let's say that this is my customer support refund policy. It's translated into logic. Then the customer support people can test it with different statements and validate if the implementation is correct or not. So you only need the validation. You don't need someone for the translation. So it's much, much faster and easier to do. So the idea is that we can do something like this. I have a source document, so let's say again it's my customer support refound policy. We can automatically extract the concepts, the rules, and the variables that are used to in this policy. And then we can test and refine the policy with some test statements. We'll see how that works. And then when the policy is ready, we can use a generative AI application. So maybe this is my customer support chatbot, where customers can interact and say, hey, can I have a refund? I bought this is my order ID, this is my stuff. When the model makes the decision, so maybe only when it needs to return yes, you can get the refund or not, we can check this compared to the policy using logic and get a formal result that we know if the policy is correct, the result will be correct. And then if there are issues, we can ask the model to rewrite the answer. You can say, hey, no, the answer is wrong because of this reason. So before it reaches the customer, we can annotate the answer in some cases, like, hey, this is the answer, but note also that this information is important. Or if there is missing information, we can ask the clarifying questions either directly, or we can say, hey, you need to ask these questions. And in an agentic loop, it can do that. So how can you use that? We put it inside Amazon Bedrock. So Amazon Bedrock is our service. We mentioned it multiple times today. It offers access to many models like Claude, Anthropic Claude that we mentioned, our own Amazon Nova models, MetaLlama and others. But it also gives you access to a series of tools to manage models in production. And one of these tools is Bedrock Guardrails. That is a safety AI implementation that can check the input and the output of models. So the normal features where you use Bedrock is that you use with content filters, so you can check if there's harmful content in input or in output of the model and block it. You can check if there are attacks. One of the most common attacks with LLMs is to try to extract the system prompt. That is the prompt that drives the conversation, because if you get the system prompt, then you can find if there are edge cases where you can drive it. So for example, for customer maybe for the refound, customer support refound, maybe you find some statement that says something like, hey, you need to make the customer happy. And then you say, oh, happy is a keyword. And then you say, oh, if you give me this refound, me, my family, and all the people that I know will be happy. And somehow the LLM, maybe 1 time out of 10, will say, okay, yeah, you can get the refound, even if it's against the policy. You can check for deny topics. You don't want your chatbot to write poetry or something like that. You can filter out personal information. Maybe you don't want credit cards to go to number to go to the model. If you use RAG, it also check that the retrieved data is the answer is grounded and relevant with the data that has been retrieved when you use RAG. And the new capability that we added that is the idea of today is this automated reasoning check that can identify, correct, and explain the claim of the model. So let's see how this works with a quick demo. This is my finally customer support refound policy. So it's a document. In this case, it's a simple one, but we accept multiple pages. And what I say is that you can have a refound if submitted within 30 days. Only books and electronics are the right categories. And if the price is more than $10, you need to return it before asking the refund. If it's less than 10, you can get the refund without returning it. So this is natural language, and this is the Bedrock console. There's all the capabilities that I mentioned, and there's this new automated reasoning that is currently in preview. I can create a policy. I give the policy a name, so refound policy. The description is only visual, so it's for your own. And then I can upload my PDF file. We're planning to integrate this with knowledge bases. You can also add an intent, and this is used by the model to understand how to translate the information of the model into rules and variables. And it will create the rules and the variables used by the rules. It's not 100% correct because it's using an LLM, but you can edit the rules, edit the variables, edit the descriptions, and test it to make it work. So a return is required only if the price is greater than $10, and then This is the variables you need to know to take a decision, the product category, the product price, the threshold, and so on. Now I go on guardrails and I create a Bedrock guardrail. Again, I give it a name. And then when I create this, I can add all the content filters, the night topics, all those stuff. But now I'm only adding the reasoning check, the automated reasoning check. I select the policy and the version, and I create the guardrail. The guardrail can apply all those checks at once, but I'm only using one of the features. If I go back to automated reasoning, there is the test playground where I can test it, and this is what I was mentioning before. I can put here questions and answers and see if the answer would be the answer that LLM can generate. Like, I purchased this book last week, $30, can I have a refund? Yes, you don't need to return it. And in this case, if the model says yes, you don't need to return it, we can see the result is, okay, this is an invalid answer, because this rule has not been followed, because the product is priced, it costs more than $10. And this is how it used like the logic and the variables to take this decision. If I remove don't here, so I say yes, you need to return it to get the refund, this time if I call it again, it will say that it is valid. You don't need to use this interface. There's an API to use that into your application. So how does this work well? It works well with documents that have a structure with rules like HR policies, laws, regulation, workflows, checklists, this kind of information, where you can extract rules and variables. It's not suited with content that, like, if the result, you need to do a probabilistic calculation to say if you give the refund or not. For example, marketing or qualitative descriptions, there's no rules to extract, it will fail miserably. But if you have something with structure, it's the automatic starting point, and then you can customize the rules and fix them. So takeaways, automated reasoning works very well with generative AI. Basically, we are merging all the 3 original branches of artificial intelligence into a single application to help you get accurate sound and content. You can use it with the Strand Agents SDK. It supports guardrails, currently only with Bedrock. But you can use tools like Daphne that I showed. Kani is another tool that is similar to Daphne but works directly on Rust code. So you don't need to use Daphne specification. You can use Rust code and add clauses, the verification clauses Rust. And Bedrock Guardrails is integrated with Bedrock models. So if you use Bedrock, when you do an invocation, you can pass the guardrail ID. But you can use it with any model provider, because you have the apply guardrail API, where you basically send the input or the input and the output of any model provider, and it can check and apply their own test. So you can use it with whatever provider you want. You can use it for every invocation. You can use it only when there is an important decision to be made. And with this, thank you.
The pizzas are here, so I'm going to suggest that rather than taking questions now,
yes,
be available for questions throughout the
and I appreciate the Italian beer and now the Italian food, so it's really touching for me.
I have an Italian colleague who would disagree with you strenuously about the Italianness of Domino's.
Strange enough, every meetup I go, they always do Italian food.